Can anybody hear anything? Because I can't.
No, I cannot hear anything.
No, no, same thing.
Can you guys hear me now?
Now we
Yep.
can hear.
Oh, okay. I don't know what's going on with that, but okay. Thank you for that. So let's begin one more time. Hello, guys. My name is Angel Sanchez Garcia, a technical consultant engineer from the VPN team. And on this session, what I'm going to take a look is on what to look on Wireshark captures for IPsec tunnels. So sorry for that inconvenience. I thought that I was on mute, but let's begin one more time. On this session, what we're going to talk about is the reason to use packet captures when we are troubleshooting and seeing the tunnel negotiation, how to apply the captures on IOSXE routers, and how to what to look once the tunnel is being created and the traffic is passing through. And in the other session, what we're going to see, it's a common scenario seen with packet captures. For example, retransmissions, simultaneous negotiations, or fragmentation, but that's going to be in another session. So first of all, guys, why packet captures? This is a feature that is very useful when we're talking about VPN troubleshooting because it can help us understand the interaction between the peers physically. For example, we can understand if a packet is being sent properly or we are receiving the packets. And it is also a good complement tool for IPsec debugging because the debug is just telling us that the logical part of the router when it's trying to process the traffic, but the captures is actually telling us that the traffic is being sent or received. And with that information, we can confirm if there's any issues with connectivity between the peers or the devices not responding at all. So those are the main reasons here. And within Cisco, we have a few useful tools that it will help us understand and manipulate the captures. So the most common one, which is everyone, a tool that we all of us use, it's the Wireshark, which is an open source packet analyzer. The IOSXE routers have embedded the monitor captures, which is a feature that will help us collect the captures packets within the routers. And also we have another tool, which is the Cisco TAC tool packet analyzer, which is very helpful to have a quick review of the output that we can collect from the routers and then extract them, change it to a Wireshark file and go and deep dive into the inside of the payload. So I'm going to just go a little bit back here to show you this tool. The link is going to be in the references for this presentation, but here you can see that it's very useful if you are not familiar with applying the captures because it gives you a quick information about how to apply the captures. And also we have a section to apply the dump, the hexadecimal dump, and then have a quick output on Wireshark as a Wireshark file. And also something very useful is that we have different platforms to work with. So in this case, we're going to talk about IOSXE, but we can also work with iOS and ASA FTD. So even though it's small, it's very useful for us. So let's go back here. And now, something that I need to clarify for you guys is that this session is intended for only regular IOSXE and SD1 IOSXE IPsec tunnels. The reason why I'm telling you this is because I am aware that SD1 is capable to create another type of tunnels that do not use IKE. They go straight to IPsec. So we're just focusing on normal IPsec tunnels that negotiate phase 1 and phase 2. So aside from that, let's just start with how to apply a capture on a router. Here, the most important part when using captures is that you need to specify the traffic that you want to filter or capture. So in this case, we're talking about tunnel negotiation. So we need to go into the protocol and understand that a tunnel is being made with UDP 500 and 4500. So for that, we need to create an access list that define the traffic that we need to catch for the UDP traffic between the peer IP addresses. So this is a quick diagram that is telling you the IP addresses of each peer, the configuration for each interface tunnel, and which peer they're pointing to. So based on that, we can collect and then specify the packet capture. I'm sorry, the access list at this moment. So the first thing is you need to specify bidirectional ways from one side to the other and vice versa. And this is very important because if you do not do this, then the capture will only collect one perspective of interaction. So you have to be careful for that. And as you can see, we're specifying UDP between the IP peers. So I'm going to go back here on this side and explain to you how to apply the capture in a moment. But so far, let's configure the access list first. It's the same topology as you guys saw just before. So if we go into the site A router, we can verify how the tunnel is configured on this side. So based on this information, we can create the capture and with the access list first. So I already have the commands here, so it can be a little bit easy. So that's the first step. We need to configure just the access list. So afterwards, what you need to do is, just one second here. We need to specify now the capture using what we just configured. So in this case, you need to specify the access list that you just configured and then the interface that you want to apply the capture to. And in this case, we need to use the interfaces that are sourced in the VTI interfaces because that's where the VPN traffic is, the VPN packets will be sent and received. So this is a quick review of how the device is going to apply the command and how we can see the output. I'm going to be a little bit more specific in the lab in a moment. But the thing here that I want you to understand is the syntax of the command, because this is something that you can adjust and actually you can customize it the way you want it and the way you feel most comfortable with. So the monitor capture, you can put whatever name you want. In my perspective, I just used CAP, C-A-P, and then you can specify the name of the accesses that you just configured. And the part that is also important and you can adjust is the buffer size in megabytes. So in my case, 10 is always been enough. Apply the interface in which you want to put a capture, and then the perspective. This is very important because you can specify also the way that you want to apply the capture for inbound packets, traffic that is coming in, outbound packets that are going out, or both ways. So since a tunnel negotiation, it's an interaction between two peers, we're going to use both. So but you can still customize it the way you want it, or be a little bit more specific, or just incoming or outgoing. But for this session, it's just this way. So I'm gonna go back to my lab here. Once I have the capture, I'm going to put the command to enable the capture. Well, to create the capture actually. Monitor capture, CAP, access list cap, the one that we just created. Buffer size 10 megabytes, interface gigabit Ethernet 1, and the perspective is both. So the capture has been created, but let's just take a look at it. Right now, it's not enabled. It's configured, but it's not running. So in order to start it, we can use the command monitor capture start. And now the device is enabling the capture. And then if something happens related to the traffic that we just specified, then the router will capture it. So that's the next slide for. We have more commands to work and manipulate the captures, and we're going to use them throughout this session and the next session. So a quick output here is, for example, the first one that I just used is to verify the status of the capture, what is configured, the access list, the size, and the status. You can start and stop the capture, and you can verify a little bit if the traffic is actually, if the router is capturing something. You can take a look at a quick review of what is captured. You can clear the capture, and the most important part here is that you can extract the information that you just collected. We have two options here. Monitor capture buff dump or the export command. Both of them provide the same result, but a little bit different. So for example, the dump command, what it does is that it extracts the hexadecimal dump that we can use and switch it to a packet Warshak file. But what it does here is that it doesn't provide you a timestamp, which in sometimes is very important. For example, when there's a slowness or a slow throughput. So for that part, this command will not be helpful. That's the reason why we could use export capture to save the output into the router memory and save it directly as a picket file. In that output, we can see the timestamp, which will be important for those scenarios. So you can guys have more clarification for that. So, but for the purpose for this session, we're going to use the dump. Okay, so now that we have the captures created and enabled in the router, now we need to understand what we are expecting to see in the captures. So since we're talking about IPv2 site-to-site negotiation, we need to understand that based on the protocol, the tunnel is going to be created using UDP 500 and 4500. So that's within the package, we need to see those references first. We also are going to take a look at the roles for each device, who is the initiator and who is the responder, and also the SPI values created. These values are unique for each tunnel that is created. It's like a session ID. So you will also see these values being created and then shared within the peers. And also within the payload, we can see phase 1 and phase 2. And for phase 1, we will see the payload in clear text. And for phase 2, it's encrypted. So this diagram is going to give you just a quick visual way of how the interaction is between the peers, about what packets we are expecting to see. I can say next request for phase 1, a response for the responder to send to us, then the phase 2 authentication request and response. So this is what a capture looks like after you collect the tunnel negotiation, extract it, and check into the router or in the Wireshark output perspectives. So in the router perspective, we can see that we have interaction, an output that's telling us that we have interaction between the two peers. However, it's not giving us that much information, but still we can at least discard that there's problem with connectivity because we have a bidirectional traffic between the peers. So you can see here that the first packet is a source from the side A, 1.1, and the second packet is coming from the side B, 2.1. And we can see that's UDP protocol. We don't know what's inside yet, but that's the reason why we can extract the values and then go deeper with with Wireshark, sorry. And here we have more information, more labels, more visible information about what's being sent and received between the peers. So I'm going to go a little bit deeper in the next slides, but I'm going to show you how we can extract this information from the router and then see it with Wireshark capture. So I'm going to go to my lab one more time. So the capture, as I told you, has been enabled. So let me just flap the tunnel. Interface tunnel 1, shut, not shut. So this is enough for me to trigger the tunnel one more time. And if I do a show monitor capture cap buffer dump, no, buffer brief, sorry. Here I can see that we have a few interaction. I don't know what this is, and that's the reason why I'm going to collect the dump, extract it, and use the tools to verify what's inside these packets. So that's what I'm going to do. I already have the capture here, the command. So this is a quick way, as I told you, to collect the output, the dump, and extract it from the router, and then transform it into a Wireshark file using the packet analyzer feed tool. So here we can copy the value, decode it. And here the tool is providing us a quick review of what has been collected, but it's not providing that much info. So that's the reason why we're going to download the capture. Let's save it. And let's see what's inside of it. So here you can see that we have the information that we need. The first packets, I'm not going to talk about them right now because the most important part at this point is the tunnel negotiation. So if I go to this packet in particular and then expand these very important parts, I can see what I just told you guys, what is expected to see, the source and the destination addresses and the UDP using the ports 500 and 4500. So up to this point, we can assume that this is a site-to-site negotiation without looking at the informational labels. And then we can take a look at the ISACAMP payload. Here we can see the initiator SPI. That is a value that it was created on the side-eye router. The reason why we do not have a responder SPI value at this moment is because that value has to be created on the remote end. And once the remote end responds to us, it's going to be populated. We have the role for this packet, and we have the type of packet that we're sending. ISA in exchange, which refers to phase 1, and then it's the request. And here, a little bit down, we have the payload of what is being negotiated between the peers. So in this case, well, I went a little bit too much here, but this is a good way to troubleshoot the VPNs. But so far, now we can understand what is being sent between each other. That's the same here on phase 2. I'm sorry, on the second packet. Now we can see that the value is the responder SPI. This value was generated by the remote end and then populated in this section. And this is the ID that it will be continue to be used in later tunnel interaction. And here we also see the packets, the payload that it's the responder is sending to us to bring phase 1. And if we go to phase 2, we see the same values again, but now we're moving to phase 2 authentication exchange request. And here, well, I cannot see further because this value is encrypted. Based on the protocol, this interaction is encrypted, so we will not be able to see what's going on. But that's the reason why we complement each other using the debugging. So this is a quick explanation of what I just did about what to look into the capture, these key parts that are important. But as something also very important is that we can use the debugging outputs to correlate what we're receiving to what the device is logically processing. So on the debugging, I just put, to get this output, I used the debug crypto IPv2 and IPsec commands. So you can see that once we receive the packet, the router is telling us that it's sending a packet to the remote end. It has this SPI value. It doesn't have the responder yet, but here we have the payload. I just
Angel,
chop it up.
we stop.
I'm sorry? Hello?
If nobody is actively asking a question, please mute yourself. Go ahead, Angel.
Oh, thank you, guys. So, well, what I was saying here is that the debugging is a good complement to the packet captures that we are seeing. So in this case, now that we receive this information, the device is going to process it, and then it's going to send the response. So this is for the first packet. Let's go to the second one. Here is the response for the other end. We have the responder SPI value now populated the same way as we saw in the captures. We have the label, the information, and everything is unencrypted here. So this way, as I'm going to be very repetitive with this, but this is something that is very helpful to understand if there's issues logically on the router once we receive the packet, or we're having issues with the connectivity and the packets are not arriving or being processed correctly on the remote end. So right now, this is just phase 1, but if we go to phase 2, we're going to see that it is encrypted. We have the same values here. SPIs, they continue to be the same. We have the roles on the debugging as well. And now it's encrypted. So this is the second part that we're seeing. And also that I need to take a look into in a few slides later, it's the NAT part here, which is a very important scenario to cover. So that's phase 2 for one packet. We send the next packet here. The responder response, and is the same, well, mostly, and then the payload is going to be encrypted. But in the debugging, well, I just chop it up because it was too much, but here you will see what's actually negotiated on the payload. So they really complement each other. So now, this is a very important scenario that I also need to cover, which is the NAT in between. So when there is a NAT here, the protocol itself has a feature to detect if there is an IP address being translated, which is not transverse. And when it does that is that we will switch from the port 500 to 4500. And well, in the debugging, you will see that, but you will also see this in the captures, which is very important to understand because from one perspective, it's going to look like nothing happened, but for some reason we switched the ports. But then on the other side, we do see another IP address, just as the diagram is here. So if I go to that type of capture, then that translation happens when switching from phase 1 to phase 2. So in this case, on the router side A, the device doesn't see any translation because he doesn't know its address is being translated. But we can see that the ports are already changed. So we can see on the packets that the port is, as he's just modified, the payload is going to be the same, but then also on the debugging is telling us that on phase 2, we just detected a NAT, so we need to switch to 4500. And then on the other perspective, we can see a little bit more clear that there is an in between because the IP address is just translated to another one. The ports are modified, and also the debugging is telling us the same. So this is just for you to know that this scenario can also happen, and this is a good key points to take a look when NAT is in between. Okay, so the thing that I just told you about the rekey, that's something that this is the last part that we can see when the tunnel is being negotiated, maintained, or rekey. So when a rekey happens is because when a tunnel needs to refresh its values. A tunnel is not permanent. It has a specific lifetime that when it's running out, both peers need to refresh those values. And that's the reason why we are going to see this type of packets, not very constantly, but we will see it at some point. So as you can see here, is using the same initiator and responder SPI because it's the same session, but we are going to see a different label here, which is a create shall essay. So with these two packets, it's enough to refresh the values, and that's something that you can also see. All right, so up to this point, what we just did is that we just covered how a tunnel negotiation is being made within the captures. But something also very important is that we can also understand how the encrypted traffic is seen through the tunnel and through the packet captures. So a quick review from here is that when interesting traffic is sent through the tunnel, it has to be encrypted, and in this case, we use ESP. And ESP, what it does is that it encrypts the payload, it adds the ESP header and tail, and adds another IP header. So for that, part, the capture that we just created is not going to be helpful. Why? Because in our access list, we just specify to collect just UDP traffic. And for this interesting traffic, then what we need to do is that we need to adjust the access list to capture UDP between these two peers. This is very important to understand because I had scenarios in which I just left the captures in UDP and I was unable to collect interesting traffic. So you need to be careful on how you are configuring the access list. So we're going to go to the lab and replicate that same behavior here. So if I do a show IP access list extended, oh no, actually show IP access list, you can see that the capture right now is just going to be specific for the tunnel negotiation. So what I'm going to do is that I will adjust it and then we can see the interesting traffic. So let me just monitor capture cat stop. No monitor capture. Monitor capture cap. Okay, we go to the access list and modify it. So something here that I need to also clarify is that the reason why I'm removing the capture and then modifying the access list is because I've tried many times to just adjust the access list and just let the capture create it, but that doesn't work. So the best option for me, at least, is that I always need to create or adjust the access list and create and delete and create the capture again. So just for you to know that you can run into those problems as well. So we are going to put the capture one more time. Let's start it. Monitor capture, cap start. Oops. Okay, so the capture is ready, and let's do a simple ping to the remote end. Well, I have a loopback interface on each side, so that's what I'm going to ping. So 10 to the source. Oh, loopback 0. So the ping worked. If we do a quick output here, show crypto IP stake SA, we can see that there's traffic passing through over the tunnel, but I don't know. We don't know what it is yet. So we can take a look at show monitor capture cap buffer brief. And now we can see that we have interaction, we have traffic sent. Well, right now we know that it is a ping, but sometimes we are unsure about that, and it's not that's not a problem because we can discard again issues now, but related to connectivity, not for the tunnel negotiations. So this is a value that we can extract and use it on the packet analyzer one more time, but I have already the capture here. So it's going to be a little bit faster. And here we can see how the interesting traffic is seen. Encrypted, yes, we cannot see what it is, but we can collect more information from this output. It's a negotiation between these two peers. It's an ESP, but take a look at what is being used, the ESP SPI. This is very important because this is also telling us which tunnel is being used to encrypt the traffic. So if I go back to the lab and if I do the same output, secret.pcksa, this output is telling me which inbound or onboard SPIs are used to encrypt and send the traffic with. So right now, obviously, they are different because it's a different tunnel, but this output, we can match it just to confirm if it's using the correct tunnel that we are expecting to see. And then another part that is very important is that since we are sending sequential packets, we can also track if there's a packet missing or a packet is not processed correctly. So for example, the ping, we have a sequence number that is going to increase for each packet. So this is for each packet that is being sent. And we can track this if we have issues with, I don't know, traffic being blocked in between or the device is not responding to specific output. So this is how we can see traffic encrypted. Let me just go back here. This is what I just showed you over the lab, and that's what we can cover from this session. So on the second session, as I told you, we're going to talk about another scenario seen with captures. But so far, I would like to know, guys, if you have any questions to what we just covered today. I'm all ears.
So Angel, I had a question in the chat. When you were showcasing the SPI values in the Wireshark capture, are these the same values that are going to show up in the CLI or different representation? Because I have run into an issue in the past where if we capture something on Wireshark, it's not always going to be the same representation in the CLI. Like let's say hex versus decimal and so on.
So you mean the ESP or SPI?
SPI.
SPI. Oh, so you have to be careful because it is a little bit confusing, but yes, I get your idea. So let me just go back here, you mean when the traffic is encrypted?
Yes, you were showing in slide 20. If you go back to slide 20.
This one.
Yes, the initiator SPI, responder SPI. Is that something that we're going to see on the CLI, or is it going to be different kind of values?
Well, these values are, it's good to clarify this because the main concern is like, okay, this SPI, does it refer to this one as well? Let me just go back here. This, where I left it, here. So these values, what they do is that they are identifiers for the tunnel negotiation, for the tunnel establishment, and for the tunnel management. So these ones are unique per tunnel. So when the tunnel is negotiated, you will see this uniquely. And when the tunnel goes down, then you will, and then a tunnel is created one more time, you will see them change. So for that part, these values are not present on the output of what of the tunnel because this is just for the negotiation. So this is more of an output that you can see on the captures and on the debugging. But the output that you see here on these SPIs is that it's just the SAs, the security associations that are created on phase 2 that are going to encrypt and decrypt the traffic. So those are very different, and they just refer to the tunnel management, but it's not related to the tunnel encrypted or decrypting traffic. I don't know if
okay, so this SPI here does not reflect the one that we're seeing in Wireshark. What about the one under show platform? I forgot the command, show platform hardware or show platform software, something about IPsec. You could look at also some in-depth SPI troubleshooting.
Show platform crypto device?
No, so that's going to be probably show platform software, SD-WAN.
I think that I will not be able to see that because this is a common routers, but let me see. SD-WAN.
Okay, I'll ping you offline on this. I don't want to.
Sure, no problem. Yeah, but the thing is that
I need to look up the command.
sure, no problem. So just to clarify what you just said, yes, you need to be very careful with the SPIs that you're seeing. But so far, take a look at when we're seeing the payload. This is what I want you to see. So this one's SPI is the securitization ID when we agree to select a cipher and encryption, and this is the identity, well, the ID that it's going to be used for this particular tunnel. So for your question is that SPI that we see when the tunnel is created is just intended for the tunnel management, not for the interesting traffic.
Okay, so we shouldn't confuse whatever mentioned in terms of SPI here versus what is on the CLI.
Exactly, yes.
Okay, thank you.
No problem. Do you have any other questions, guys?
Yes, Angela, I want to ask you something. Actually, I would like to ask you why we're using the physical interface instead of the tunnel for the captures.
Well, that's a very good question. And actually, I didn't want to go deep into that, but you forced me to do that. So we can put the capture on the tunnel interface, but what it's going to happen is that we will have a different perspective of the traffic flow. So, and it will depend on what you're trying to capture. So the reason why we are on this whole presentation, the reason why we're using the interface that is sourced in the BTI is because that's the physical interface that the traffic is going to be sent through. So when the tunnel is negotiated, we still do not have the tunnel up. So we cannot see anything at that moment related to the tunnel. But when the tunnel is up, what we can do is that we can put captures on the virtual interface and then capture the interesting traffic in clear text. However, this is the tricky part. I have some colleagues from SD-WAN, and they just told me that that feature to apply the captures for SD-WAN IPsec tunnels is not possible to do because they say that it doesn't give you a correct output. But at least for the troubleshooting of a normal site-to-site for the VPN, you can put it just to confirm what's going on with the traffic, the interesting traffic. But related to the tunnel negotiation, that's not possible on that interface. So you can, but it's for another purpose. If you want to take a look at if the interesting traffic is passing through, then yes. But if you want to take a look at the tunnel negotiation, that has to be on the physical interface.
Yeah, Demetrius, to your point, you would want to capture on the tunnel interface itself if you're looking at the unencrypted traffic. And for an example that we had in the past, a customer was traversing or sending EIGRP neighborship over an encrypted tunnel, and we were trying to troubleshoot why the EIGRP neighborship was flapping. And the only way to do that was to capture on the tunnel interface, not from the physical one. So as to Angel's point, you're looking for the tunnel negotiation, so that will be the physical interface.
Exactly.
I hope that makes sense.
Yep, it does. And something here very important, just to, again to clarify, is that that type of capture on the BTI, it's for more specific issues when we have more traffic in the tunnel that we cannot understand what it is, and we need to see what is exactly the traffic that we want to take. But for this example, it was just a ping. So, but yes, there is another issues, for example, that we have a TCP missing or ERGRP. So applying the capture on the BTI is just to see if the traffic is passing after the tunnel is up. Yes.
Okay.
Any other question, guys? Okay, I think there is no more questions. And well, the last thing for me is that I want to thank you guys for your time and for your patience on this record and on this presentation. And I am sorry for what happened at the very beginning. I thought I was unmuted, but mistakes can happen. But I'm glad that you were able to take a look into this and see what you can do with packet captures and Wireshark. It's a very powerful tool. And this is just for VPN, but imagine what you can do with other type of traffic. So I hope to see you in the next session where we're going to take a look at common scenarios of site-to-site VPNs now with captures. That session is going to be a little bit more related to the lab side. So I'm hoping that I have everything ready for that session. So thank you so much again, guys, and have a nice day.
Thank you so much, Angel. That was a very helpful session.
Thank you guys as well for your time.
Bye-bye.
Thank you. Bye.
Oh, and also, I know that you guys are leaving, but for the questions that you have on the chat, I wasn't able to respond them right now, but I will send their answers on the next email with this presentation. So thank you so much again.